Yeah.
Sweet, cool. Or should I just go for it? Let me just share my screen. Um, cool. Sweet. Can everyone see my presentation?
Yes, we can see.
Sweet. All right. So I think I've got a pretty small room in here today. So I'm just going to go through it. And if anyone wants to stop me and ask questions, feel free to. About a 10-15 minute presentation. So I'll go over my work today as a PhD candidate. So my name is Brian Gu, and thesis topic is optimization of inductive power transfer pads for in-road EV charging. So the contents of the presentation, I'll start with an introduction to our group and the work that I'm doing, and then go over the research motivations behind my work, and then introduce you to some of the things that I've been working on to date. So for those of you who aren't familiar, we've got quite a large power electronics research group at the University of Auckland. It's had quite a long history researching wireless power transfer, mainly focusing on inductive charging, starting with pickup handling applications and then moving into the EV charging space. So we've got multiple professors at the group, and some of whom branch off, like Patrick, who is looking at capacitive power transfer. And this slide I've taken here from Dr. Dilipa Thrumawathana, and just to give you an idea of the scale of the group we have in Auckland. But apart from that, I'm just going to jump straight into the research that I'm doing. So I don't think you need me to tell you that there's a high uptake of electric vehicles, which is driven by sustainable development goals, as well as policy and investment in EV infrastructure. So we're considering the problem of wired plug-in chargers, which are inconvenient and require handling of electrical equipment and wires. So we're looking at the opportunity to apply inductive power transfer to EV charging, which will give electric vehicles a significant ergonomic edge over ICE vehicles. And in the figure on the left, we can consider the stationary case for EV charging. And the reason I make that distinction is because I'd like to talk about that there is also the opportunity to extend inductive power transfer to EVs to the dynamic case shown here. So charging an electric vehicle while it is in motion. And this has several further implications. We can address the battery problem of electric vehicles, particularly heavy-duty electric vehicles like trucks, which carry large onboard batteries. And we can alleviate the range anxiety of EV owners associated with long-distance travel. However, we also have some challenges associated with in-motion charging, namely cost for larger scale deployment, the robustness of in-road charging modules, and the different power requirements of road users. So to provide a quick overview of an IPT system for EV charging, power is drawn from the grid and rectified and converted to high frequencies by an inverter, and this supplies a primary pad which generates a single-sided magnetic field. So underneath the vehicle, we will intercept this magnetic field and provide power, which is regulated to the battery. So the focus on my work is the magnetics of the system, particularly the primary magnetics, so the pad that may be embedded in the road or mounted on the surface of the road. So we talk about IPT pads then. These generate and receive the single-sided magnetic field and consist of a flat wound coil with high permeability magnetic material underneath, and in some cases shielding to block back field. So there are several metrics we can use to assess these IPT pads. We could consider coupling to another pad, which is the ratio of incident to transmitted magnetic field, or we could consider the leakage magnetic field that humans are susceptible to in the vicinity of an active charging system. So ferrite is used in IPT pads to significantly improve the coupling and reduce the leakage field. However, it has its downsides. It's brittle, it's expensive, and there are few options to recycle. So researchers have looked at reducing ferrite in IPT pads. The figure on the left shows a heuristic approach, basically taking ferrite out in sections where a low reluctance path is not so required. And figure 7 shows an optimization driven approach to reduce the thickness of the core layer in a double D pad. We are considering the opportunity to look at soft magnetic composites. So the ferrite-based SMC on the top right with quite a high ferrite volume fraction has a lower magnetic permeability. However, as you can see from the information on the bottom, it is up to 20 times higher failure strain than ferrite, which is ticking off our mechanical robustness criteria. So then what are the research motivations behind my work? Ferrite should be reduced is what we've identified, particularly for in-road IPT pads. And as mentioned, with the opportunity to explore soft magnetic composite materials, which have reduced permeability but improved mechanical robustness, this could be something that could be used in IPT pad cores. And also there's the opportunity to improve optimization methods for IPT pad design. So now I'll present some of the work that I've been doing in my PhD. So the first thing is considering an optimized core layer for the primary charger of in an IPT system for EV charging. So we'll consider the double D coil as a candidate solution for its good coupling and misalignment tolerance. And we can see two different designs for the double D on the right, one with a full ferrite core layer and one with a ferriteless so without a core, sorry, no comments, sorry. Okay, so, and then moving on from that, we'd like to identify an optimal design, and this might be a core layer with some SMC and some ferrite, which achieves our design goals of good robustness, good coupling, and reduced leakage field. So we'd like to make these decisions by an optimization process due to the multi-objective design variables that are in play here. So we're applying a genetic algorithm in SGA2, which has been shown to produce fast, efficient, and diverse solution space. So applying FEA simulation to evaluate these designs can be a slow process. So we've implemented parallelism and caching to speed up the runtime of the optimizer. And we're evaluating our designs based on ferrite, coupling, and leakage as design objectives. So a good design should have high coupling, low ferrite volume, and low leakage. So here are some results showing the likelihood of core material placement after we've run the optimization. So we wanted to have a look at where did core material end up being placed in the core layer of the double D pad. And you can see ferrite converges to the center where it channels, where it's underneath the main flux channel for field shaping. And the SMC converges around the outside where it is used to contain the leakage magnetic field. So if you think of ferrite in terms of the higher permeability magnetic material and SMC as low permeability, the ferrite is in the high field density regions. So this is the meat of the work. This is the results, the Pareto front from the optimization, if you will. So this is there's a lot of information contained here. So on the x-axis is the coupling factor of these designs to a full ferrite double D secondary, and on the y-axis is the leakage field of the system. And the color indicates the volume of ferrite in the primary pad, and the size of the dots indicates the volume of SMC in the primary pad. So to identify some trends from this, we can see that as ferrite volume increases, the coupling factor increases and the leakage field reduces, which is consistent with our understanding of why we use ferrite. And also the size of the dots of SMC is quite large. So this indicates that our designs are using SMC. So if we identify a design from the minima, design C, and compare that to the full ferrite double D, we can see what is the benefit of producing this ferrite SMC hybrid design. So comparing design C with the benchmark full ferrite primary, we see that design C replaces 61% of ferrite with SMC and achieves 67% reduced leakage. This is only requiring a 3% sacrifice in coupling. And when we tested these in systems transferring 3 kilowatts of power, we only observed a 0.8% efficiency reduction, DC to DC, with the design C system compared to the full ferrite double D system. So clearly this is a design game of trade-offs here, but design C has achieved quite desirable low cost and good mechanical robustness from a small sacrifice in other properties is what we are showing here. So I'll present another piece of work to you today before I finish up. So we also looked at doing a neural network optimizer. So as I mentioned, FEM is a slow process despite the parallelization. And our neural network provides an opportunity to displace FEM as a surrogate model. So we'll consider a search space, the same core layer search space we considered earlier, and varying the coil parameters of the double D pad. And I'll explain to you a bit more about a neural network. So a neural network is a nonlinear mapping of input variables to output by arbitrary computational algorithm. So we'll need to set weights for the neural network. Oh, sorry, there's a chat message. 4 minutes left. Thanks, Dheeraj. Yeah, we'll need to set weights for the neural network, and this will require training data from ANSYS simulation. So ANSYS cannot be entirely displaced, however, we can alleviate some of the computational effort. So what does this look like? This looks like an augmented design framework. So on the right, you can see that the FEM simulation is required to collect training data to train the neural network, and then we continue with the surrogate model optimization. And then at the end, we can take the optimal designs and reevaluate them with FEM and allow for high accuracy selection. If I can change the slide, there we go. So the neural network, we wanted to do some evaluation of this method then. So on the left, the Pareto fronts you recognize from the earlier slide. On the left are the neural network predicted design objectives. And on the right, the designs which have been re-simulated with finite element method simulation. And we can see the designs closely match. The benefit of this neural network optimization method is only for this neural network, only 2,000 were required to train the data. So with the large search space, this could look like a saving in computation time from months to weeks to days. Although, as you can imagine, there is some optimization, there's some designer judgment that goes around here to how much, to the stopping criteria, the convergence criteria of the genetic algorithm. So I can discuss more about that if you like in the questions after, so I'll just continue. And the optimization criteria can be varied, which is a big benefit of the neural network. So if you incorporate all the training data you have available, it could be a matter of just changing some of the design objectives or changing the weighting you provide to design objectives. So future work, we'd like to evaluate SMC, continue the evaluation for higher power, and also look at what role it might play in an in-road wireless charging system. And before I finish up, I'd like to just mention the work you've seen today. You can read more if you're interested on IEEE Explore. My first publication is up, although the second, I think, is still yet to be up. It's recently presented at conference. And if you want to discuss more about the work I've presented, please feel free to reach out. Part of the reason I am here today is that I am in the US for 3 months. So, anyone working in and around Logan, please feel free to connect. And I'd love to make use of the time here before I return to Auckland to engage. So cool. I'm happy to take some questions if Dheeraj says I have time.
Yeah. We have a couple of minutes for questions.
Cool.
Please feel free to ask any questions to Brian.
No questions? I must have explained everything perfectly then. It's good for me.
Yeah, Brian, I have a quick question. So,
Yeah, sure, go for it.
how does SMC compare with ferrite in terms of cost? You said SMC is better in terms of robustness, and probably you have also shown that uh, like there is not much reduction in coupling and all.
Yeah, good question. So, how does it compare in terms of cost? So SMC does use 74% ferrite. I think there's a lot of what ifs to answer this question. So perhaps this is the best slide. So SMC does have 74% ferrite volume fraction. But if we can use recycled ferrites, so the SMCs are crushed ferrites, which are bonded with resin. So if we don't need to have an intact ferrite structure, if we can just use crushed ferrites, potentially there is the opportunity to use recycled ferrites, and also I mean that would have to be realized on a mass scale, I think, to realize lower cost there. But currently, I would say it's still 3/4 ferrite, so it could be expensive. But I think there's the opportunity to realize lower cost IPT pads.
Okay, so is cost also a variable in your optimization, or you're not considering cost as of now?
Yeah, good question. So cost is it's part of the three criteria we are considering optimization at the moment are coupling, ferrite volume, and leakage. And I would say cost is partly captured under that ferrite volume objective, based on kind of some of the ideas if we can use recycled ferrites, SMCs would be lower cost. That's the extent to which it's captured, though. Cost can be included. It's more a method we're proposing than an absolute design procedure.
Nice, thank you. Yeah. Sorry, are there any questions for Brian? Otherwise, we can proceed to next presentation. Okay, thank you, Brian.
Thanks so much. Cool.
Yeah, Sonak, I guess you can start now.
Sure, thanks. Oops, sorry. Yeah, okay. Hello, everyone. I'm Shonak from Cornell University. I'm a fourth-year PhD student here in EC. And today I'll be presenting some of my work that I've done on developing high-power dynamic capacitive wireless power transfer systems. So capacitive wireless power transfer systems are like a parallel path to the traditional way of wireless power transfer, which is using magnetic field-based inductive systems. So our group was one of the first groups to start work on capacitive systems, and we have been targeting high power applications like EV charging. So today I'm going to talk in length about what are the different challenges involved in capacitive WBT systems, and look at some of the system design and optimization trade-offs, and present with some results. So this is an outline of my talk. So as we all know, I mean, wireless power transfer systems can lead to widespread adoption of electric vehicles in the near future by enabling stationary, semi-dynamic, and dynamic charging. In particular, the focus of my work is on electric field-based WBT systems, which is the capacitive systems. And the reason why we think this has great potential is because these systems can be much lighter, inexpensive, and smaller than the traditional inductive-based systems, because due to the unidirectional nature of electric fields, we do not need any flux guidance materials such as ferrites, which makes the systems low cost and smaller, and making them easier to embed in the roadway. Now, one of the challenges in capacitive systems is if we want to transfer power using electric fields, due to the smaller value of the permittivity of free space, we need a very high frequency of operation of the systems to transfer high amount of power. And that comes with its own challenges, because at this high frequencies, we are typically talking about ISM band frequencies such as 6.78 or 13.56 megahertz. So you have different parasitics, and transferring power at high efficiencies at these frequencies is challenging. So that's what our work has been on. So first, let's look at the heart of the system, which is where the wireless power transfer happens, which is basically the couplers. So if we look at a typical EV charging application, we have lots of parasitic capacitances. So the yellow lines here denote the actual charging pads, which are implemented as two metal plates. We have one pair of plates for the forward path and the other pair for the return path. However, apart from the main capacitance that we want, we have different kind of parasitic capacitances. Now, and all of that takes away power from being transferred to the rectifier side or to the output side. So we developed a unique design approach that can help us to absorb all of these parasitic capacitances into this equivalent 4 capacitor model, which is established through circuit symmetry and some clever circuit design techniques. And that helps us to take advantage of these parasitic capacitances and without their detrimental effect. So we designed or we proposed the design of a novel charging pad for capacitive systems that incorporates the effects of these parasitics and absorbs them so that we can use them for system design. Then we looked at the design of optimal matching networks. So on either side of these capacitive couplers, what we have is known as matching networks. Now they help in two things. One is they help to provide reactive compensation that is needed to cancel out the impedance of these couplers. And they also help to step down the displacement currents in the wireless charging environment. So outside the vehicle, you do not want any fringing electric fields because there are strict field safety concerns. So the matching networks on either side help to step down the input and input current so that you have very small displacement current. So we can do a design optimization so as to maximize the system efficiency. And using those results and some other modifications in the charging pad design, we can get a good target system efficiency of around 90%. And we can optimize other parameters of the charging pad so that we fall or meet these specs. So we went ahead and validated the design of these charging pads. And this was a 13.56 megahertz per system, and we were able to get a peak efficiency of 92% while transferring 2 kilowatt power. Now let's also talk about the fringing field reduction part. We said that we want to limit the fringing of the electric fields because we do not want the fields to be emanating out. One possible approach is to use like convex curved plates, but that adds one more dimension. It's difficult to implement. So what we want to achieve is basically a field distribution like the convex curved plates, but with planar designs, and which is what we call the meta surface based couplers or the meta couplers, where we use some impedance sheets so that they can support tangential electric fields, and that can help to shape the fields as we want them to. So then we implemented we physically implemented this metacouplers using distributed impedance models. So here they are implemented using distributed or lumped inductors, and you can see the results. So the electric fields using the metacouplers, which are shown in the blue and the green, are much lower than the traditional conventional couplers, which are shown in red. And this metacouplers can be implemented using both capacitive and inductive reactances. And we find out that the inductive reactances lead to a much higher separation of electric fields, although we take a little bit of hit in system efficiency, but that's within the design limits. So we went ahead and validated it experimentally, and we found that for this design, we were able to reduce the fields at the edge of the coupler by 40%. So now that we have designed the couplers, let's look at another challenge which is present due to the high frequency operation. So you basically have the power electronics on the curb, and you have the charging pads, which is typically underneath the vehicle, and you need to connect them using some connecting wires. Now at this high frequencies, the length of these wires could be substantial in terms of the frequencies, and they can add a lot of impedance, which can be detrimental if we do not model them accurately. So we found out a clever way to actually use these parasitics of the wires and incorporate them into the system design. And we basically want to implement these wires as transmission lines. So if you consider a parallel plate waveguide, you can model the impedance of these lines so that they can provide the necessary reactive compensation and also provide a voltage gain. And these are the exactly two or the two conditions that are met by the matching networks. So if we can accurately, or if we can cleverly model the size and shape of this connecting wires, we can basically eliminate the need for a primary side matching network. So you eliminate entirely the discrete inductor and the capacitor that you had, and you just have a set of parallel plate or parallel wires that run through from the inverter to the charging pads. And using this, we were able to demonstrate basically the same operation as you would have with a discrete inductor and capacitor. So that's a good thing. Now let's look at some performance enhancements. So one of the challenges that we have due to this high frequency operation is that we have to use wide bandgap gallium nitride transistors, and typically these transistors are not rated for very high power. So here is shown the maximum power processing capability as a function of the loss per transistor that can be handled using GaN devices in a high frequency inverter. And you can see they are limited to typically like 2 or 3 kilowatt power level. Now, if you want to compete with inductive systems, which have been like 50 or 100 kilowatt, or even with standard onboard chargers, we need to scale up the power. The chart here shows that already we are kind of in the 2 kilowatt range, and we are an order of magnitude better than the other state-of-the-art systems in terms of power transfer density. But we want to target even higher power numbers. So for that, the approach that we will take is basically combine the output of multiple transistors. So basically paralleling the transistors, or paralleling the inverters in this case. However, paralleling at these high frequencies is non-trivial because slight mismatches between the parallel transistors can result in asymmetries and loss in system efficiency. So we designed and proposed few power combining architectures that can help to combine the output of multiple inverters and lead to also balanced current sharing between them. So we proposed 4 different architectures. I'll not go into the details. You can take a look at our papers. And then we compared their performance in terms of maintaining a constant output power in the presence of mismatches. And we find out that an emittance network-based power combiner is the best power combiner in this case. It helps in balanced current sharing and also maintain a constant output power. So we also did some analysis, and we found out that in presence of other mismatches between the two inverters, you can also maintain almost a flat power profile. Now, using this design, we implemented a 6.78 megahertz 12 centimeter air gap system, and using that, we were able to transfer 4.2 kilowatt DC to DC power, which is double of what we did earlier. And this is a record for a capacitive system at this large air gaps of 12 centimeter. And this approach is highly scalable. So we validated it for 2 parallel inverters, but it can be scaled to n number of inverters as the need be. And finally, let's also look at the dynamic charging performance. So we also want our systems to be dynamic, because then you can reduce the size of the onboard battery and bring down the vehicle cost. So instead of charging like at a time, you can charge on the go. Now that comes with its own limitations. For example, you have misalignments when the vehicle is on the move, and you can also have vehicles with different floor clearances. So we proposed an innovative solution to that, which is known as the active variable reactance rectifier. And this helps to maintain a constant output power and a system efficiency for certain ranges of misalignment and varying floor clearances. And the idea there is that if you have misalignment between the roadway side and the vehicle side charging pads, then you can adjust the voltages of these 2 power splitting branches that you have, and by a proper design, you can basically compensate for the change in the coupling capacitance, and you can provide like an inductive capacitance or inductive reactance here. And that can be done by controlling the voltages, which basically controls the power that is being processed by each path. And you have like equal impedances on both of them. And we also accounted for the output capacitances of the devices on the rectifier side, so that we can get an in-phase current and voltage at the input of the AVR rectifier. Now, so we talked about the matching network design when we were designing the couplers. So with the AVR rectifier, that imposes an additional constraint. However, the target here is to maximize efficiency as well as also maximize the maximum misalignment tolerance, which means that you want to have a constant power for as much misalignment as you can possibly have that the system design allows. So we can design system design flowchart for that, and we can also accurately find out what should be the voltages for each of these power splitting branches for each value of misalignment. And this can be basically implemented using a closed loop control. So you do not need to actually calculate this. You could either implement it using a closed loop or a lookup table. And this shows the performance across air gap variation. So yellow is basically when you have 100% normalized output power, and you can see that using this AVR system, you can compensate for plus minus 50%, and you can also compensate for floor clearances or road clearances of 6 to 16 centimeters, which is almost double. So we went ahead and experimentally validated a 12 centimeter air gap based system. This shows the results. So without the AVR rectifier, we had like this red plot of power versus misalignment. With the AVR rectifier, you have this blue chart. And with the AVR rectifier, we are able to transfer 90% more energy to a vehicle, which is almost double, and shows the working of this system. So to summarize, in capacitive WPD systems, because of their high frequency of operations, we need to incorporate the parasitics present in the charging environment. So we proposed a novel charging pad design. We also proposed metasurface-based metacouplers to reduce the fringing electric fields, and found a way of leveraging the parasitics of the wiring to our benefit. We also looked at different power combining architectures and proposed misalignment tolerant based dynamic capacitive WPD system. Here are some of my conference publications. Here are some of the transactions. And I'd like to thank the sponsors of this work and my collaborators for this. Thank you. I hope you'll like the work, and please feel free to ask the question, any questions you have.
This is Prabhakar. Is this time for questions?
Yeah, we can take a couple of questions.
Okay, yeah, thank you. First of all, great work and great presentation. And is it a continuation of what Khurram Afridi was doing?
Exactly.
Okay.
Yeah,
okay.
yeah.
So a couple of questions. One is, look like the limits on the power capability were imposed by the gallium nitride transistors, but I expect they'll get better, as well as this pairing that you can do, or paralleling.
Right.
So what is there a limit, as you see, in terms of how many you can parallel with the current state? Could you go up to 20 kilowatts, or what is there a limit, practical limit currently?
Yeah, so exactly. So with this kind of a emittance network based power combiner, there is like no limit. So currently, like, we are targeting like a very high power system, typically like around 40 to 50 kilowatt capacitive WPD system.
Okay.
We have done some preliminary design, and we do not see any limitations as to practical limitations as to implementing multiple parallel based inverters.
Okay. And then the second question, I guess, when you say percent misalignment, I'm not sure I understand. What does 50% misalignment mean?
Right. So if we look at this figure, so based on the dimensions of the coupling plates or the charging pads, So 100% misalignment means when the two plates are like just separated out
I
laterally.
see. Okay.
So basically, depending on the dimensions, that is like percentage with respect to
Okay.
the center.
And
of
the plate compared to the floor pan of the vehicle is about.
I think most of us are back now.
Might want to give
Oh.
it just one more minute. It looks like a couple of rooms are still trying to close out.
Trying to leave. It's hard to leave.
Is it hard to
So much
leave?
information. No, I'm just saying there's so much great information.
Awesome. Let's see here.
Hey, Don, while we are waiting, is it okay to continue with the question that kind of got cut off mid-sentence when you switched back?
Go ahead.
Yeah, so Shaunak, just trying to see, I don't know what the size of the plate is compared to the floor pan in feet or meters. What is the approximate size of the width of the plate? And therefore,
right. So right now, we with the power transfer density of like 60 kilowatt per meter square, we have a like a pad or which is like a feet in length, and the dimensions of the coupling plates are like 22 centimeters. So it's roughly like 70% of the total size of the backing plate.
Okay, understand. And then the last question, have you done a comparison of the the inductive transfer system versus yours?
Exactly. Yeah. So we have done like a theoretical comparison of inductive and capacitive systems, and it turned out that at the frequencies that we are operating at, like 6 to 10 megahertz, I mean, kind of we can get similar kind of efficiencies as the inductive systems at the power levels that we want to target.
Thank you.
Thank you.
Okay. Well, welcome back, everyone. And real quick, I think we'll have each of the moderators give us a quick recap of their sessions. And I do believe all the sessions were recorded for viewing later on if you weren't able to attend one of the sessions. Correct me if I'm wrong on that, but they should be available for viewing. So we'll have the moderators give us a quick recap so you can see what's happening. And we'll start with Dheeraj, and then we'll go to Connor and then Arahi. Just a minute or two.
Yep. Yeah, so in breakout room 1, we had like 2 exciting presentations. First one was given by Brian on the optimization of inductive charging pads. And he has shown that like soft magnetic materials have improved robustness when compared to like traditional ferrite materials. And he has presented an optimization technique like in using both these magnetic materials, such as like soft materials and traditional ferrite materials, so that he can get good robustness and good coupling without compromising on the leakage flux and all. And he has shown that the charging pad designed using his like presented approach have comparable performance with full ferrite double D charging pads, and like there is also no reduction in efficiency and all. Later he has also presented a neural network-based optimization approach in order to reduce simulation time in comparison with normal FEM simulations without having a compromise on accuracy. And now coming to the second presentation that was given by Sonak Maji, which is on capacitive wireless power transfer systems for EV charging. He has shown a way to design capacitive wireless charging systems, how to design matching networks efficiently, and also how to leverage parasitics in the charging environment and wire parasitics into the charging pad design and matching network design. And he has also presented some techniques of where through which we can reduce fringing fields in the air gap so that we can maintain electric field, like fringing electric fields within the safety limits. And later, he has also presented some power scaling approaches to how to scaling these capacitive wireless charging systems to higher powers. And he has shown some 4.2 kilowatt capacitive wireless charging system results, and to this date, like 4.2 kilowatt is the highest reported power for capacitive wireless charging system. And in the end, he has also presented some dynamic compensation techniques so that like misalignment performance of the capacitive systems can be improved. And he has shown that the dynamic compensation techniques can maintain like constant power transfer for plus or minus 40% misalignments. So these two were like exciting presentations, and yeah, if anyone did not get a chance to attend these presentations, we'll have recordings later, so they can watch it later.
Thank you. And then Connor.
Yeah, let me share my screen real quick. Can you all see this?
Yes.
Okay, yeah, Oscar did an amazing job. In our breakout room was all about the Indiana pilot project, and specifically the accelerated pavement testing facility and everything that they've built there and all the tests they've been doing there. So Oscar talked about how some of the objectives from his project was actually constructing these pavement sections in this accelerated testing facility, as well as investigating the mechanical and thermal basically strain on these pavement sections when there is a dynamic wireless charging system embedded. So at the INDOT facility, they built two different segments. They built an asphalt pavement section using a PCC material within the charging unit. And they also built a concrete pavement section using the magnet concrete. They also did a lot of modeling with finite element analysis models to kind of predict the loading and the stresses that would be on these different pavement sections with this dynamic wireless charging embedded. So some of the critical measurements that they took when they were doing these experiments was the transverse and longitudinal strains on the concrete and asphalt, some compressive stress as well as vertical stress. They're basically monitoring all of the different aspects of when you put this dynamic wireless charging system in the roadway, and then you have cars driving over the center edge and corner of where this pad is embedded. How is it affecting the concrete and the pavement, and how is it affecting the charging unit? Oscar went through in very good detail how the concrete and asphalt sections were constructed, including where the charging unit was placed, what materials they used, and how it was constructed. And he also discussed the tests they've been doing, some falling weight tests, static load tests, some traffic load tests, a lot of these involving actual wheels running back and forth over these concrete and asphalt sections over and over for 1,000 passes a day over these pavement sections. Their goal is to reach 100,000 vehicle passes over these pavement sections by the end of the year, and use all of that data that they collect with different strain sensors and things like that to be used in the Indiana pilot project, and to basically help us understand in more detail how these dynamic wireless charging systems affect the durability and maintainability of the roadway.
Thank you. And then Arhim, if you're able to give us a quick recap of your breakout.
Definitely. Okay, let me share my screen quickly. Okay, so first of all, I just want to say congratulations to the team from USU that have been selected as finalists for the International Future Energy Challenge in Hanover, Germany, which is one of two teams left from the US. So congratulations again. This would culminate their experience for us that they have been going through since over a year ago, since they submitted their proposal and presented at the APIC conference in Orlando, Florida. So pretty much they have been working on a design for a single phase solid state transformer, which is comprised of 3 stages, of course, going from AC to DC and DC to DC again, and then DC to AC. And, you know, as the transformer works, this is to provide isolation to protect other electrical components. So for this competition, they were required to meet operating criteria set by the conference, and they will be going through a process of inspection in which, for the competition, someone will pass some pros and we'll see if they pass the operating criteria, and then the results will be compared to the other participants. However, they did some additional work, right? So one of the things that they did is to aim for a price of $200 or below for the component cost, and also work for advanced capabilities, such as a steady-state power transfer up to 600 watts, the autonomous control of the solid-state transformer, and also the bidirectional power transfer. It is important to mention that this team was comprised by undergraduate and graduate students from 2 different backgrounds, from electrical and mechanical engineering, and they have been working on the design of the circuit, of the PCB systems, the simulation, the testing, and also the hardware prototyping. Some of the goals that they have for the future is to increase the efficiency of their system and to decrease its volume. And lastly, they are currently working on testing and improving the completed design for the final competition that it's to come. So congratulations again. That's pretty much it.
Thank you all so much. They were incredible presentations. I just have a couple little announcements I'm going to go through, or updates. So we have on July 12th coming up, there will be a center-wide meeting to go over the Student Leadership Council SWOT analysis of our most recent cohort trip to Washington, D.C. And next month, we will be focused on the Aspire Technology Showcase, including a couple of the inventors talking about their inventions. And then, as Don mentioned at the beginning, on September 20th and 21st, we will be having the Aspire Industry and Innovation Day annual meeting here at the University of Colorado Boulder, where there will be a lot more opportunities to network with the Aspire students. Seems we don't have that many minutes left, so if you have any additional questions, or if you would like to reach out and connect directly with one of our presenters, but you don't have their contact information, you can reach out to Dawn or myself, and we're happy to connect you. I'm putting my email in the chat right now. In addition, their presentations will be uploaded to the site later on, so we're really excited about that. And one last thing, if you guys could give us some feedback, there's a link to a survey. It's just 2 questions. It's posted in the chat. You guys could take a minute to fill that out. That would be wonderful. It really helps a lot. And then I just wanted to say thank you for all of those who attended, and a special thank you to our presenters today for all the important and amazing work they're doing and for taking the time to present it to us. Is there anything else, Don?
No, thank you so much. I think it was a great presentation by all. And just last, that we recorded the sessions and they should be available on the site in the coming weeks. Thank you all for joining the Tech Talk today.
Great session. Thank you.
Let's see, who do we got here? Turn your cameras on, guys, so I know you're here. That would be great. Are we all here gathered? Is everybody? I feel like we're missing somebody.
I think we're missing Luke, maybe.
Yeah, I don't see Luke. Maybe he had to run off to something really quick.
Yeah, Luke was on break from his internship, so he had to go back right away.
Oh, he's got to do real work. What a bummer, man. So how'd it go, guys? What's your feedback? There were, just let you know, I wasn't able to, I popped into one room really quick, and then all of a sudden I had people coming into the main room looking to be directed. So we had 4 or 5 people that came in throughout. So how did it go? How did you feel it went?
I thought it went pretty good. I popped in and out of all of them, and I thought the presentations were going really well, and I wasn't able to stay for the whole time, nor did I completely understand everything because I don't have that much of a technical background, but they seemed to understand what they were saying, and it was amazing. So
I imagine the presentations were pretty good. As far as the rooms went, number 1 weighted as not a surprise, if we have to say, was the pilot in Indiana, had a few more. Then we came in, second was the power electronics guys, and then the third one was IFEC. I kind of thought IFEC, and this is one of those things, guys, don't feel bad about it. After they hear the summary of what you guys are doing, all of a sudden you can be sure people are going to be interested in what you did. They just didn't know what it was. So not that you'll have a second bite at the apple, but I think, for example, in our annual meeting, it's going to be a great opportunity to have a poster and have an opportunity to showcase that as well. So you have a second opportunity at it. Okay. How were the questions?
Yeah, I mean, there were quite a few questions in my breakout room, and yeah, like presentations were quite engaging.
Yeah, I think we could have used some more questions from the public, maybe.
Yeah, we did not have enough time for the questions in the end, so I like one guy was asking in the main room, so.
Well, those were both a couple of weighty topics to try and do in one time. So I was just kind of, but you know, my view is don't discourage motivation. So if you guys came with that proposal, we should do it. And if we feel like, again, we have opportunity in the future where we can put things in front of folks, we can do it again. And my view is our next opportunity for this type of showcase is the annual meeting, Industry and Innovation Day. And we should think about how we do this, because I know we quote have the poster session, but I think we need to be a little bit innovative about how we want to put things in front of members and cultivate discussion. So it isn't just one of those generic look at a poster. You know, we got to find a way to market and kind of put things out that's out there and stuff. So you guys are quiet. I'm not feeling the love. Oscar, you were kind of the Academy Award winner, and I'm not hearing anything. So.
Why? No, I had a lot to say, so I really had to run through it. So I didn't have too many questions. I bet I had more, but I had so much to compress in such few time. But actually, regarding what you were saying, wouldn't it be pragmatical to do the exact same thing we just did right now, but in person, like having different rooms and different presentations in person for the annual meeting?
Well, what we're doing is we're going to have workshops. So during that, there's going to be on the Wednesday. Do you guys mind? Do you guys have time? We'll walk through really quick what's happening in the annual meeting. Maybe you can think about it. Do you have time or not? Like 3 minutes, 4 minutes. Yeah.
Yeah.
Yeah, we're good.
So Elena and Zainab are on our planning committee. So they kind of have all the details, but I'll give you the high level and then filter back through them your inputs as well, because they represent you on the planning committee as well. And you can always come to me. But to your point, we call it Industry and Innovation Day, but it's kind of spread across 3 days. So Wednesday, people will be arriving in Colorado Springs, or not Colorado Springs, shoot me in the head, in Boulder. So they'll be arriving in Boulder in the afternoon. And that afternoon and evening, there are 2 interactions. One is with the National Science Foundation is doing their on-site review of Aspire. So the National Science Foundation people will be there. And then later, we kind of figure we'll have a session later where the IIB members then will also go in and look at it. But that afternoon session is really around what we call poster sessions. But for me, it's not just what we're doing with the center, but it's what we're doing with these projects. We can have any number of posters that we want, and we can organize it in the way that we want. The only challenge that we would have, Oscar, is saying, let's have a session dedicated to NDOT. You know, that not sure how the flow But and you don't know me that well, but I think the analysts who work with me suffer. My view is we should think creatively about how we want to do it. Let's not be put into a box. So when we say poster session, let's not think poster session. Let's see, what can we do different? How do we organize this in a way that's different? That, yeah, we have to have posters, but how do we create flow? Maybe there is an opportunity and you guys can bring a proposal and say, that's great, but maybe on Wednesday or on Thursday, and we'll talk about, there's kind of this additional networking session. Maybe you want a second bite of the apple where we have specific student generated projects, so there's opportunity to think about how we want to format it. But the high level is Wednesday, people show up and they have this student engagement with the poster session. Then Thursday is the industry and innovation day, where it's going to be based around basically 4 workshops with purpose statements. And don't ask me what the purpose statements are, because we're still trying to refine what it is. But one session specifically is led by the Student Leadership Council, related to skills and workforce development. So one of them will be really led by Student Leadership Council with an IIB member. So it's co-joined, right? The other 3 sessions we're coming up with purpose statements. But to your point, all of the feedback we get from people is really about the pilots, electrification of roadways. So there's going to be some work kind of in through there as well. So we have that. We'll have those. They'll be broken up. So we'll have 2 sessions in the morning, 2 in the afternoon. We'll have lunch. We'll have breaks. And then in the evening, we'll have kind of some networking activities and then a dinner. Then Friday morning, this is a bit sensitive, so hang on to this. We're arranging for people to visit NREL. But there's a big but. And the big but is focused on our industry members and not on the Aspire members, because number one, we have a limit of the number of people who can go to NREL. They've already told us can't go above a certain number. And the second thing is they're planning for internal meetings for Aspire on Friday. So they basically want to keep us internally. Don't ask me what the agenda is on that, because I'm not working on the internal Aspire meeting agenda. So if you think about industry members will show up late Wednesday, interact with students, interact with other industry members. We'll have workshops on Thursday. And then Friday before they fly out, they'll go to NREL. Those who want to go to NREL can go to NREL based on the limit of people we have. But during the Thursday, there is another session in the afternoon. And many of the members have said outside the poster session, we wanted another opportunity to have other conversations with students. So we can think about what a networking opportunity, what would be an activity at kind of the end of the day after the workshop sessions of what we could do. Was that sufficiently boring for you all? Michaela just nodded her head, yes. Thank you, Michaela. That was nice. Says that sufficiently boring? You went, yeah, it was. Thanks.
No,
All
no,
right,
that was
got it.
interesting. It sounds like something to definitely prioritize.
All right, thanks. Thanks for recovering. I was worried, like, is it boring? Yeah, it's physical boring. Yeah, I think. Right.
No, it's a lot of logistics. I do see the picture now.
Yeah, but I'll tell you what, verbally and on paper, people seeing what we're planning this year, on paper, it really looks good. We have a lot of execution things, like you said, the logistics and execution, but on paper, the idea you come in, you network, you poster. When Thursday, it's not just going to be panels sitting there, bore. It's going to be, well, let's discuss, let's look, let's analyze, have another networking session. Oh, and I get to go to NREL before I fly out. Sounds like a pretty good offer.
So it'll be different than last year's?
Yeah, shoot me in the head if it's like last year's, okay? So yeah, it'll be different than last year. The idea is to create more of a dynamic dialogue and have discussions and not presentations. So even the tables, and this is one of the things and then I'll shut up and let you guys go, or you can ask questions. But even the idea that we're going to meet together in a room and you'll have tables, but Alvaro, who disappeared because he's getting ready for something today, I don't remember but Alvaro brought up an idea that we like, is that what we would do is with the tables, we're going to have students already pre-assigned to be kind of there at the table as a student table leader, but also we want to have IIB members, quote, sponsor that table. Now with industry members, you have to be careful about using the word sponsor because they think they have to pay for the table. And that's not what we mean. What we mean is that they would you'd have the John Deere table. It would be moderated by John Deere. It'd be moderated by AECOM. It'd be moderated by, so people would actually see, oh, this is the table these were. So when you go to sit during these workshops, you'd actually say, oh, I want to go sit the White-Tristy table, or I want to go, then that person from White-Tristy would be there and would be the table leader and moderator. So that we're trying to do things a little more innovative. I don't know if it's going to work, these crazy ideas we come up with, but we're trying to shake it up so people are a little more engaged, have ways to do it. And the other thing with the 4 sessions is you're not going to be sitting with the same people on the table in every single session. You got to move tables. We're going to create a mechanism, not sure yet how it's going to be, but Jaron and Michaela, you're not going to sit by each other all day. All right. That's all there is to it. You got to go out and meet people, break out of your zone or something. All right. Any questions, further input or comments? And then we'll kind of summarize here.
I just wanted a quick thing about the poster sessions. The SLC, Zainab was talking about doing kind of a review or like having a little Zoom meeting so we can all kind of practice presentations and poster stuff if people are worried about it before the meeting. So if that's something you guys are interested, please reach out and let us know kind of what you're looking for with that. But just as it gets closer, thought some prep work wouldn't hurt. So.
All right. And going back to our meeting today, you guys really are our gems within Aspire. I mean, we have 2 what I call gems. One are number 1, and this is not BS, guys. I'm not saying this for right. Our student talents are our diamonds, our gems, right? That's number 1. Number 2 is whatever research and technology that we're working on. And the third one is information in general. So today it was kind of a 3-fer. You're able to show the students, talk a bit about the projects we're working on, right? And they got information. So that's one reason why I really like these sessions, where I think we need to improve. And this is where we need feedback. We discuss, we need a better way to market out to some of the IIB members so they understand what's there. And hopefully in the annual meeting, they'll kind of catch this. And the second one is we have on paper about 200 Aspire participants and only 25 show up. So there's also kind of an something internal. And I think students are Aspire participants. Some of that is leadership. So it's not just students, but some of the ready leaders that I know are traveling. But one of the things I think we need to do better is also word of mouth with the student population is some of these tech talks, especially the student showcase as well. These are really interesting things to see what other students, other people are working on stuff. So probably have to market better externally and internally. The number of people that showed up today by the way, was on average what we've been having the last 7-8 months. It's not much different than what we've had. So I just feel like the potential is close to 100, to be honest. And that's kind of a goal that I have in mind. But anyway, any last comments other than?
Yeah, can I make a quick last comment? Is it all right if we just hold off on uploading the presentation so I can make a few quick changes? I mean, the recording's fine, but just checking some of the image rights on the presentations before we upload them to the website.
Yeah, absolutely. If you could forward your presentation to Luciana, right? Lou, you've asked for it, right? So that would be awesome. Hey guys, thank you so much. Thanks for all you do and you contribute, and more to come, more fun to come. All right.
Thanks,
Thank you for the information.
See you
Thank
around.
you.
Take care.
Thank you.
Thank you.